This video begins our discussion on climate, and to do that we are going to use this acronym up here, L.A.M.E.C.O.W, where each letter is going to represent a different climate factor, something that can affect the climate of an area, making it warmer, cooler, wetter, drier, certain conditions that it can expect to see all year. So L.A.M.E.C.O.W is a word we're going to hear a lot, with each letter representing a different factor of climate. Now, before we start talking about climate, we definitely want to make sure we know what it is, and the difference between climate and weather is going to help us do that. Now, climate we want to think of as long-term. Alright, so climate is long-term, and when we're talking long-term, we're talking 30 plus years. So we're looking at the average weather conditions in an area for 30 plus years and bringing in all that information of temperature and precipitation. We can then figure out, well, what is this area usually like? Again, long-term. So the things we have to consider are temperature, right? Is it generally warm? Is it generally cool? What is that long-term 30 plus year average? We also want to look at precipitation. Okay, is it generally wet? Is it generally dry? Is it a desert? Is it monsoons? Lots of rain? And within those two, we want to look at their seasonal changes. Okay, do I see a big difference between the summer and the winter? Do I see a small difference? What is that seasonal change within those averages? So I put a picture of Florida on here because we kind of have an idea of what the climate of Florida is like without even looking at the data, right? You plan a vacation to Florida because we know usually the average temperature is warm. The average precipitation is not much, right? We know we're going to get sunny skies there. Yes, it can rain, but it's definitely not going to be a vacation spot that rains every day. Okay, so climate, we're thinking long term. What is it normally like there in that area? In the case of weather, we're then thinking short term. Okay, for instance, what is happening currently, today or this week, right? We see a weather forecast on the news. We don't see a climate forecast, we see a weather forecast. What's it like today? What's it like tomorrow? The rest of the week? Doesn't go out very far. When we get a weather forecast, it's really short term. Here's what it's going to be, and then we're moving on. Okay? Just because an area has warm climate doesn't mean it couldn't get a really cold day. These are things that happen short term. They come, they go, and they end. Okay? Now there's a lot of different types of climate classifications. Here's a map labeling a bunch of the different types of climate. And really, this German scientist Koppen has a really specific way to classify the climates. Just like looking at what type of climate, we definitely start with temperature. And we also start with precipitation. Those are definitely the two main factors in determining climate. But the third one Koppen brought in seems a little bit different. It's native vegetation. And vegetation, of course, is just a fancy way of saying plants. So what type of plants are native or naturally found in that area is going to clue me in to what type of climate. So if you think about it, here I've got a picture of an area with its native vegetation, which of course here is the cactus. So what kind of climate are you going to assume you have here because of this native vegetation? You're automatically, hopefully, going to think desert. Now the reason why these plants are so important to telling about climate is because plants need certain conditions. They need certain temperatures and they need certain amounts of precipitation. A cactus here is only going to grow in an area with little precipitation. It won't really survive in an area with a lot of rain. Definitely not a lot of snow. Okay, so native vegetation helps key me in to these other two factors, temperature and precip. If this plant can exist here and its conditions needed are this, that's going to be the type of climate found. Okay. So again, Koppen came up with this classification system. There's a lot of different types of climates. We got humid, we got marine, we got desert, tropical, continental, tundra, ice. Okay, but zooming in on Minnesota on the right-hand side there, does ask, what is Minnesota's climate going to be? Okay, so if we zoom in on Minnesota in this general region, we are pretty much considered to be humid continental, where we have warm summers and cool winters. Okay, we are in the middle of the continent, hence its name continental, but we hold a lot of moisture, so we do get warm temperatures in the summer, which of course we are thankful for. So now that we know a little bit about climate, what climate is, we want to now start thinking about all the things that can change it and affect it. And again, the acronym here we're using is L.A.M.E.C.O.W. We are starting today with just L.A.M.E.C.O.W. So take a look at each of the factors that can change a climate. The two we're going to focus on today in this video is latitude and air pressure. But we will learn about mountain barriers. How do mountains affect a climate? How does elevation of a city or area affect climate? And then continental location, where it is on the continent, either inland or on the coast, definitely has an effect on the climate that it sees. So again, our focus today, latitude and air pressure. Pause if you need to get all those filled in today. Now starting with L is for latitude. We all have studied latitude before. Latitude, of course, are the horizontal lines on the globe. Sometimes people think about it with this little reminder. They're like a ladder ring, so we call it latitude, kind of as a way to help remember. You're climbing up the rings like a ladder. Okay, but they are horizontal across the globe, and there's a couple important latitudes that we want to point out. One of the most important ones right here is running right through the middle of the earth, and that of course is the equator with a latitude of 0 degrees. It runs right through the middle of the planet, therefore that is my 0 degrees latitude. Now in terms of us, for Minnesota, that's where the second line is drawn in, that I tried to add there. We are right about halfway in between the equator and the poles. And if we look ahead here, the poles are right around 90 degrees at the tip top of the globe. The equator, of course, is at that 0. Minnesota is right in the middle at 45 degrees, and we call that 45 north because we are then north of the equator. There's a corresponding 45 south this direction, but of course we live here, so that's the part we are focusing on. Now the further you get away from the equator, the higher the latitude number goes. Okay, so as I move away from the equator, I notice those latitude numbers rising, whether I'm going up or down, right? So here I'd get 10, 20, 30, 40. The numbers are getting bigger, but now I'm going south of the equator rather than north. Okay, so latitude are those horizontal lines, and they do really clue us in to what's going on with the temperatures at these different areas. Now this is something that I know you've heard of before. Using these keywords, hot, warm, and cool, see if you can fill in the areas here as either hot, warm, or cool based on where they are relative to these key points. Of course, here's the equator, the 0. Way up here, these are the poles at 90 degrees, and then of course in between, right about where Minnesota, we're at the 45. So what label, hot, warm, or cool, would you give to the equator there? Hopefully you're reaching for your red pen. This is definitely the hottest part of the planet, right there on the equator. Okay, where we have the poles, the 90 degrees, the furthest away from the equator, that's definitely going to be my cool zone. I kind of got cut off down here. This is my cool zone. Right in the middle then, the 45, I'm going to use my final word as warm. Okay, and again, we know that living in Minnesota, We've got really warm parts of our year, and we've got really cold parts of our year. So we're right in that zone that can kind of go either way. So the average ends up being warm. So why is that? What is happening to make the globe have that uneven heating? Okay, latitude is a factor due to the uneven heating of the Earth. Depending on where you're looking at the Earth, here's my equator again, 0 degrees. Depending on where you are, the sun is hitting at different angles. And of course, the sun is what heats the Earth overall. So that's our most important thing we have to consider. The sun heats the Earth overall, whether we have direct rays, this is going to give me the most heat, or indirect rays, this is going to give me the least amount of heat. Okay, depending on what type of solar rays we have is going to directly relate to my average temperatures or my climate. Now, places that get direct rays, where they're almost at 90-degree angle, like this guy right here, these are my direct. Okay, when I have direct rays, those typically fall on the equator. And that energy then is more concentrated. I'm getting more solar energy to that spot, so then I tend to see the warmer temperatures there. Other areas have slanted or indirect rays. Those are angles that are less than 90 degrees, so just like this one, indirect. Okay, those indirect rays are less than 90 degrees. They fall on my higher latitudes. And the higher the latitude, the less direct the ray is, the overall cooler the temperature is. So hopefully you came in today knowing the equator was the warmest, but maybe not sure why. Now you know it's because the equator has the most direct rays, almost 90 degrees, throughout the whole entire year. Whereas the higher latitudes have those indirect rays, giving them less concentrated sunlight, not heating them up as much. So you got this little diagram on the right-hand side. Label which one are your direct rays and which one are your indirect rays. And again, you're looking at the angle. So here, I see almost a 90-degree angle, whereas here, my angle is much smaller. So this is less than 90. This is 90. Figure out which term is going to match as far as direct or indirect rays. Hopefully, you determine these are your direct rays right at the equator, giving me then warmer temperatures overall, where then these here are my indirect. Less than 90, cooler temperatures overall. Okay, so what does that mean for the Earth? Well, during the summer months, in July here, we then see that the Earth is tilted towards the sun. So if you go ahead and draw in your axis there, along with your equator, that's your 0 line, most of the direct rays are hitting above the equator. Okay, so that means for us, this is our summer. Right? We have the warmest temperatures in the summer where the most direct rays are hitting us up here at 45 degrees. But over here in January, this of course would be the winter, when we are then tilted away from the sun and our most direct rays are hitting below the equator. Okay, that would then give the southern hemisphere their warm months, while we here are in the opposite. As the Earth goes around the globe, there are of course two other seasons. We have fall and we have spring. Okay, in each one of those, the sun hits mostly on the equator. So we're kind of in that transition time from really hot over here in our summer months from all the direct rays, and from our really cold over here from the indirect rays. We are then transitioning during those other 2 months of fall and spring. Now notice here the distances from the Earth. During the summer months, we are actually further away than in the winter months. So you have a question there on the side. When is Minnesota closest to the sun? It's actually when we are in winter. Okay, we are closest to the sun during the winter months, but we are cooler because of the tilt of the Earth and the more direct rays hitting the southern hemisphere. So a lot of times people say, oh, we're closer when it's warmer, but that is not the case. Okay, we are closer during the coolest times because the Earth is tilted away from the sun. So latitude has everything to do with our seasons. Okay, same kind of image here. All right, so quick on our seasonal differences. We, of course, have the summer solstice. Summer solstice is our longest day of the year, and that's where the direct rays hit in the northern hemisphere on June 21st. So right on the northern hemisphere line, about 45 degrees, that's when we have the most direct rays, and that is typically our warmest time of the year. In terms of our winter solstice, when we are tilted away from the sun, the most direct rays then hit the southern hemisphere, so they are warm here while we are cool up top. Those are our winter months, typically happening December 21st. For both spring and fall, the sun's rays usually hit on the equator, giving the warmest temperatures to those locations, sending warm kind of transition times to us up here in the northern hemisphere. Okay? So latitude is our L. Moving on to A for air pressure. Air pressure is caused also by this uneven heating. Because the Earth is heated and cooled in different areas, different materials heat faster and slower, and therefore start to cause these pressure differences around the Earth's surface. Now, just a quick thinker for you. We got some choices. Think about which one of these in each combination heats up faster. Go ahead and pause, give yourself a circle, and then come back and see if you've got it. When we're thinking about soil or water, soil is going to heat up faster. The water, when the sunlight hits it, it's going to go all the way through, trying to get all the way down to those bottom parts of the water. It's going to take longer to heat the water. In terms of shiny or dull, a dull item is going to heat up faster because shiny is simply going to reflect the material.
Please excuse this interruption. Just a reminder that tonight is the District 196 College Fair, this year hosted at Egan High School from 4 to 6. Please feel free to attend the Rosemont High School District 196 College Fair, hosted at Egan High School from 4 to 6. See you there.
When we're thinking light or dark colored surfaces, dark are going to heat up a little bit faster. The darker colors absorb more light, as do dark soils where the snow will reflect most of that solar energy. Okay, so different surfaces on the Earth are going to heat in different ways, again causing this uneven heating to make both areas of high and low pressure. Now thinking back to our chemistry unit a little bit, what is the density of warm and cold materials? Warmer temperatures are going to have their molecules spread much further apart. So if I were able to grab a box of warm air, I would see their molecules are pretty far apart. Where in the terms of cold temperature items, their molecules are bunched much closer together. It's not that they have more molecules, it's just that they are huddled closer together. Okay, so in terms of molecule density, we can definitely see that the cold air or the cold material is more dense. It's got more particles combined together, squished together within this one space. So if we keep that in mind, what's going to happen when we have an area of high pressure? When I have this area of high pressure, what I end up with is air that is typically cooler. Okay, so I see my temperatures start to drop as that air sinks down. This air lacks moisture. Heard the saying before, maybe high and dry. That's a saying we're going to use a lot in here. high and dry area. If the pressure is high, we typically have a dry environment. Okay? It lacks precipitation, like rain, making it that dry environment. And we usually end up seeing a clear sky then because, again, of the dry and no rain factors. This air is sinking down. The particles are more close together. It's got a higher density. High pressure sinks. It's pushing down on the Earth's surface. In terms of low pressure then, we have a warm air starts to rise. And if we think back to convection inside of the mantle, we know that warm air rises upward. Okay, as that warm air rises upward, it's available to hold more moisture. As we think about those particles being spread further apart, there's more space for little water molecules to peek in there. So the warm, low pressure tends to hold more moisture, and what I end up seeing then in this type of pressure system is clouds and precipitation. And that precipitation can vary depending on the temperature, whether it's snow, ice, water, rain, different things there. So do a little predicting on the right-hand side, thinking about your densities of the different temperatures of air. Here's a little visual over here for you. Got a higher temperature box of air here, and a lower temperature box of air. What type of balloon is going to rise, hot or cold? Now I hope you know the answer to that just based on your background knowledge, but the question here is why? Okay, think about something that has to do with the density of the air molecules. Bring that in to your answer. Go ahead and pause while you write your answer there. As we move on, just a little bit of comparison between air pressure and other factors. If I notice my air pressure is decreasing, then I can expect to see an increase in the following factors. Temperature. If temperature goes up, I know I'm going to see a decrease in air pressure. Same thing with elevation. Elevation or altitude, if I'm going up a mountain, I'm going to notice that the air pressure is lower up top.
Noah Susanat to the choir office. Noah Susanat to the choir office, please.
Humidity also will increase as air pressure decreases. We call these things an inverse relationship. Okay, they are inverse relationship because it is opposite. If one thing goes up, the other thing goes down. That is an inverse relationship. And it works both ways. If I see air pressure increase, I know temperature is going to decrease. Again, a couple practice problems for you to answer there on the right-hand side. As air moves up a mountain, we know the air pressure is going to lower. And there's your right-hand questions, a little bit of practice for you. Fill in the blank with either an L for low pressure or an H for high pressure. Go ahead and pause while you answer those questions. And finally here, we want to look at the globe and figure out overall, where am I going to start to see these wet and dry areas on the globe based on the type of air pressure that is fairly consistent in this range. Okay, we know at the equator here, at 0 degrees, I tend to have warm temperatures. What does warm air do? Warm air definitely rises, so I have this labeled as a low pressure system. Now in a low pressure system, because that warm air rises, do I have wet or do I have dry air? As that warm air rises up, it starts to spread out a little bit, allows for more moisture to come in. This is definitely a wet type of a climate. Okay, low brings in wet climate. So it says labels the wet and dry areas. Low is wet, as is at the 60 degrees. This is a wet climate. But in terms of the high pressure system, high air we know is cooler. Therefore, the cooler air sinks. Sinking air stays dry. And we talked about that little slogan there, high and dry. So both at the 30 degrees And at the 90 degrees, we want to label that as dry. And if you were to look at a map, this is where we would see some of the world's largest deserts. The Sahara in Africa, right around 30 degrees latitude. And you might think, oh, there's no deserts up at the poles, Ms. Chumley, but Antarctica is one of the biggest deserts on the earth. Deserts is referring to the dryness of the climate rather than the temperature. Okay? So, challenge question for you there on the right. Where would I get heavy rain showers more likely then? Would that be happening at the equator or at 30 degrees? And give me a why, including something about the pressure there. Okay, so again, take a pause and answer that question. Finally, thinking about the storms that we have. Typically, we see storms happening during areas of low pressure. We can get climates that are apt to more storms, but just up here in Minnesota, we have low pressure systems that bring storms as well. The most common storm we can see from that, of course, is a thunderstorm. But depending on the conditions, tornadoes and hurricanes can also occur when those two air masses meet, when the cold meets the warm. So a lot of information here within both latitude and air pressure. Okay, once you have the video complete and you've got all your side questions answered, do not forget to go back to your summary questions at the end. Latitude is questions 4 through 6, and air pressure is questions 7 through 10. Now that you've got the notes for that, you want to go ahead and complete those questions on the back. Check in for another video on mountains, elevations, and continents soon.